Core iron losses. The transformer's magnetic core is like a steel bicycle brake. Every time the magnetic field swings back and forth, the steel grains have to rub against each other. This is hysteresis loss. It is proportional to the frequency F and to the peak flux density B max raised to an exponent n, usually between 1.5 and 2.5. A simple expression is pH equals kH times F times B max to the n times V core, where kH is a material constant and V core is the core volume. Eddy current loss is similar to a boat moving through water. The changing flux induces circulating currents in the conductive parts of the core, and those currents dissipate energy as heat. The loss varies with the square of frequency and the square of flux density. PE equals KE times B max squared times F squared times V core. KE depends on the lamination thickness and electrical resistivity. By cutting the core into thin insulated sheets, laminations, we break the large circulating loops, just as baffles in a river slow down water eddies. In practice, a transformer designer adds both components to get the total core iron loss. P core equals pH plus PE. Real-world example: a 50 kilovolt ampere distribution transformer may have a core loss of about 500 watts at 60 Hz, meaning that even with no load it still consumes power to keep the magnetic field moving. Copper I²R losses. The windings are like the heating element of an electric kettle. Current I flowing through the copper resistance R produces heat, according to the familiar I²R rule. At no load the current is small magnetizing current, so copper loss is tiny. When the transformer supplies load current, the loss grows rapidly because it depends on the square of the current. P copper equals I² times R. R itself is not constant. Copper resistance rises with temperature. R sub T equals R sub 20 times open bracket 1 plus alpha open bracket T minus 20 degrees Celsius close bracket, where alpha is approximately 0.004 per degree Celsius for copper. If a winding heats from 20 degrees Celsius to 80 degrees Celsius, its resistance increases by about 24%, so copper loss also rises by the same factor. I equals S divided by open bracket square root of 3 close bracket times V for a 3-phase transformer. Hence, for a 100 kilovolt ampere, 11 kilovolt transformer delivering full load at unity power factor, I is approximately 5.2 amperes per phase, and copper loss may be a few hundred watts. If the same load runs at 0.8 power factor lagging, the current is higher, approximately 6.5 amperes, and copper loss increases accordingly. Stray load losses: when flux does not follow the intended path, leakage flux, it cuts through nearby metal parts such as the tank, clamps, or even the winding supports. This creates small eddy currents and extra I²R heating, called stray load loss. Think of a flashlight whose light leaks around the edges and warms the surrounding plastic. The stray loss can be broken into two parts. Leakage flux eddy currents, proportional to F dot bleak squared and the volume of the conductive parts. Circulating currents in windings, caused by non-uniform current distribution, especially in multi-layer windings. A practical rule of thumb used in design is P stray is approximately K stray times P Q full load, where K stray is typically 0.02 to 0.05, 2% to 5% of full load copper loss. For a transformer whose full load copper loss is 400 watts, stray loss might add another 8 to 20 watts. Though small, it becomes noticeable at high loads and must be included in efficiency calculations. Efficiency eta is the ratio of useful output power to total input power. Eta equals P out divided by the sum of P out, P core, P copper, and P stray. No load idle condition. P out equals 0, input power approximately P core plus a tiny magnetizing copper loss. The transformer still draws a small current called magnetizing current. Full load condition, P out equals rated apparent power times power factor, often unity for calculation. All loss components appear. Rated load efficiency, usually defined at the nameplate rating and a specified power factor, for example 0.8 lagging. Example: assume a 200 kilovolt ampere transformer, rated voltage 11 kilovolts, with core loss equals 600 watts. Full load copper loss equals 1,500 watts. Stray loss equals 10% of copper loss equals 150 watts. At 0.8 power factor lagging, output real power equals 200 kilovolt ampere times 0.8 equals 160 kilowatts. Total losses equals 600 plus 1,500 plus 150 equals 2,250 watts. Input power equals 160 kilowatts plus 2.25 kilowatts equals 162.25 kilowatts. Efficiency equals 160 divided by 162.25 equals 0.986, approximately 98.6%. If the same transformer runs at unity power factor, copper loss drops since current is lower and efficiency rises to about 99%. This illustrates why efficiency curves are highest near full load and moderate power factor. Voltage regulation and its influence on transformer efficiency. Voltage regulation, VR, tells how much the secondary voltage changes from no load to full load. VR% equals V no load minus V full load, divided by V full load times 100. It is caused by two voltage drops, the resistive drop I times R and the reactive drop I times X, where X is the leakage reactance. The expression can be written as V full load equals V no load minus I times R times cosine phi plus X times sine phi, where phi is the load power factor angle, cosine phi equals power factor. A high VR means the secondary voltage falls a lot under load, so the utility may have to increase the primary voltage, which increases core loss because core loss rises roughly with B max squared. Moreover, to keep the voltage within limits, designers may oversize the core, adding more iron loss. Hence, better regulation, lower VR, usually leads to higher efficiency, especially at light loads where core loss dominates. Sample problem: a 50 kilovolt ampere transformer has V no load equal to 415 volts, R equal to 0.5 ohms, X equal to 1.5 ohms. At full load, current equals 73 amperes with power factor 9/10 lagging, phi approximately 25.8 degrees, compute V. I times R times cosine phi equals 73 times 0.5 times 0.9 equals 32.85 volts. I times X times sine phi equals 73 times 1.5 times sine, 25.8 degrees, approximately equals 73 times 1.5 times 0.435, equals 47.6 volts. V drop equals 32.85 plus 47.6, approximately equals 80.5 volts. V full load equals 415 minus 80.5, approximately equals 334.5 volts. VR equals open bracket 415 minus 334.5 close bracket, divided by 334.5 times 100, approximately equals 24%. A 24% regulation is relatively high, indicating the transformer would be less efficient at light loads. Improving regulation, for example using a larger core or tighter winding layout, reduces the I times R and I times X terms, thus lowering VR and raising overall efficiency. Effective load factor and power factor angle on efficiency. Load factor LF equals actual load divided by rated load. Power factor angle phi equals arccosine of power factor, which determines the proportion of reactive current. Copper loss varies with the square of total current. I total squared equals the quantity P divided by V times PF, all squared, plus the quantity Q divided by V, all squared. Where Q equals P times tangent of phi, which is reactive power, expanding gives I total squared equals P squared divided by V squared times PF squared, times the quantity 1 plus tangent squared phi times PF squared. Thus, for a given real power P, a lagging power factor, which means a larger phi, raises current and therefore copper loss. Analytical expression for efficiency as a function of load factor and power factor. Efficiency eta of load factor LF and power factor PF equals LF times P rated times PF, divided by LF times P rated times PF plus P core plus LF squared times I rated squared times R times the quantity 1 plus tangent phi squared times PF squared plus P stray. Numerical illustration. Take the 200 kilovolt amp transformer from the previous example, with rated real power 200 kilowatts at power factor 1. Core loss 600 watts, copper loss at full load 1500 watts, stray loss 150 watts. Case 1, load factor 0.5, power factor 0.9 leads to rated current full equals 200 kilowatts divided by square root of 3 times 11 kilovolts, approximately 10.5 amperes. Actual current equals 0.5 times 10.5 divided by 0.9, approximately 5.83 amperes. Tangent phi equals tangent of 25.8 degrees equals 0.48. Copper loss equals 5.83 squared times R times the quantity 1 plus 0.48 squared, where total resistance equals 1,500 watts divided by 10.5 squared, approximately 13.6 ohms. Computing gives copper loss approximately 5.83 squared times 13.6 times 1.23, which is about 560 watts. Total loss equals 600 plus 560 plus 75, the half stray, approximately 1,235 watts. Output equals 0.5 times 200 times 0.9, which is 90 kilowatts. Efficiency eta approximately 90 divided by 90 plus 1.235 equals 0.986, which is 98.6%. Case 2, same load factor 0.5 but power factor 0.6, phi approximately 53.1 degrees, tangent phi equals 1.33. Actual current equals 0.5 times 10.5 divided by 0.6 equals 8.75 amperes. Copper loss equals 8.75 squared times 13.6 times the quantity 1 plus 1.33 squared, which is approximately 8.75 squared times 13.6 times 2.77, giving about 2,800 watts. Total loss approximately 600 plus 2,800 plus 75, which equals 3,475 watts. Output equals 0.5 times 200 times 0.6, which is 60 kilowatts. Efficiency eta equals 60 divided by 60 plus 3.475 equals 0.946, or 94.6%. The example shows that a lower power factor, meaning a larger phi, dramatically reduces efficiency, especially at light loads where core loss is comparable to copper loss. Temperature rise, cooling methods, and their impact on losses. The transformer's temperature theta is a balance between heat-generated losses and heat-removed cooling. The basic thermal equation is theta rise equals P total divided by U, where U is the overall heat transfer coefficient watts per degree Celsius. Oil immersed natural convection, ONAN, U approximately 1.5 to 2.5 watts per degree Celsius. Oil immersed forced air, ONAF, U can reach 5 to 8 watts per degree Celsius. Oil immersed forced oil of or oil flooded with external pumps, U greater than 10 watts per degree Celsius. Because copper resistance rises with temperature, see R sub T formula, higher theta causes higher I squared R loss, creating a positive feedback loop. Designers limit theta rise to about 65 degrees Celsius for dry type and 80 degrees Celsius for oil type transformers. Exam type calculation. A 75 kilovolt ampere ONAN transformer has total losses of 2 kilowatts at 20 degrees Celsius ambient. If the allowable temperature rise is 65 degrees Celsius, determine the required overall heat transfer coefficient. Theta rise equals 65 degrees Celsius results in U equals P total divided by theta rise equals 2,000 watts divided by 65 degrees Celsius, approximately 30.8 watts per degree Celsius. Since typical ONAN values are about 2 watts per degree Celsius, the transformer must be sized with enough surface area or use radiators to achieve the needed U. Cooling also affects core loss because increased temperature reduces the magnetic permeability slightly, causing a small increase in hysteresis loss about 0.3% per degree Celsius. In high-temperature environments, the designer may select a core material with lower temperature coefficient, for example grain-oriented silicon steel, to keep core loss stable. Thus, efficient cooling not only protects the insulation, but also limits the growth of both copper and core losses, preserving high efficiency. 150 kilovolt ampere, 22 kilovolt transformer has the following data. Core loss equals 800 watts constant. Copper loss at full load equals 2,500 watts at 1.0 power factor. Stray loss equals 5% of copper loss. Cooling is ONAN with allowable theta rise equals 55 degrees Celsius. Energy cost equals 10 cents per kilowatt hour. Open parenthesis a close parenthesis plot efficiency versus load 0 to 100%. For each load percentage L in decimal calculate. P out equals L times 150 kilowatts times power factor. Assume power factor equals 0.9 lagging. I equals L times full load current. P copper equals L squared times 2,500 watts. P stray equals 0.05 times P copper. Eta equals P out divided by the sum of P out, 800 P copper and P stray. L equals 0.2 leads to P out equals 0.2 times 150 times 0.9 equals 27 kilowatts. P copper equals 0.04 times 2,500 equals 100 watts. P stray equals 5 watts. Eta approximately 27 divided by 27.80, 5 approximately 97.1%. L equals 0.5 gives P out 77.5 kilowatts. P copper equals 0.25 times 2,500 equals 625 watts. P stray equals 31 watts. Eta approximately 96.2%. L equals 1.0 gives P out 135 kilowatts. P copper 2,500 watts. P stray 125 watts. Eta approximately 94.3%. Connecting the points gives an efficiency curve that peaks around 0.4 to 0.5 per unit, load approximately 96.5%. This is the optimum load point, where marginal increase in copper loss outweighs the gain in output. Open parenthesis B close parenthesis economic loss analysis dash. Assume the transformer runs 4,000 hours per year at 0.6 per unit load. Annual core loss energy equals 0.8 kilowatts times 4,000 hours equals 3,200 kilowatt hours. Annual copper loss energy equals 0.6 squared times 2,500 watts equals 900 watts, which is 0.9 kilowatts times 4,000 hours equals 3,600 kilowatt hours. Annual stray loss equals 0.05 times 0.9 kilowatts equals 0.045 kilowatts, which is 180 kilowatt hours. Total annual loss equals 6,980 kilowatt hours. Cost equals 6,980 kilowatt hours times 10 cents equals $698 per year. If the owner can increase the load to 0.8 per unit, the yearly loss becomes copper loss equals 0.8 squared times 2.5 kilowatts equals 1.6 kilowatts, which is 6,400 kilowatt hours. Total loss approximately 8,000 kilowatt hours equals $800. The extra $102 per year is justified only if the additional revenue from the extra 0.2 per unit of load exceeds this amount. Open parenthesis see close parenthesis temperature rise check dash total loss at full load equals 800 plus 2,500 plus 125 equals 3,425 watts. Required U equals 3,425 watts divided by 55 degrees Celsius, approximately 62 watts per degree Celsius. Since typical ONANU about 2 watts per degree Celsius, extra radiators or a switch to ONAF, U about 6 watts per degree Celsius would be needed to keep the temperature within limits. These combined problems illustrate how core loss, copper loss, stray loss, voltage regulation, load factor, power factor, and cooling all intertwine to determine transformer efficiency, optimum operating point, and economic feasibility.